to learn about section 4.1, which is exponential functions. A little bit of graphing, a whole lot of math, pretty simple stuff. I think that this is not going to be too painful for any of us. So let's start with Thomas's. Well, this is only Thomas's, of course. This is Thomas's. Let me write that up here. That might help. There we go. We're starting out by looking at the difference between regular functions we've been doing and exponential functions we've been doing. The two examples he gives you are y equals x squared and y equals x cubed minus 1. Notice that we have exponents for those. The variable is the base number, not the exponent. So those are just normal functions we've dealt with before. What we're looking at in this section, in this chapter, looks like that or that, where the exponent is the variable. That's an exponential function. That's the difference. Notice the exponents are numbers in our regular functions that we've looked at before. In this case, in this chapter, we're going to see exponents that are variables. That's the huge deal. So this would be an exponential function of base 2. This would be an exponential function of base 3. I don't care how you say it. That's not a big deal. Okay, let's look at Get Ready section, where we're looking at A, B, C, and D, and looking at negative exponents. I think this is a reminder to you. 2 to the negative 3. A negative exponent says to the base, move me, move me, move me, move me, move me. Just keep saying it until you move that base. He's in the numerator right now. We're going to move him to the denominator. And the negative will go away on the exponent because we moved him. We did what it was telling us to do, move him. And now, of course, 2 to the third power is 1 over 8, and that's the answer. B is 4 to the negative 1. Again, this negative exponent is telling you to move this base. Move me, move me, move me, move me, move me. And I hope that's really annoying and that you remember it because of that. So when you see the negative exponent, you don't get hung up on what am I supposed to do? You'll hear me being annoying like that. You'll move that 4 to the bottom. And of course, 4 to the first is just 4. C is 7 to the 0 power. That's just a 0 exponent, means the answer is 1. Anything raised to the 0 exponent is equal to a 1. It's just one of those things that's kind of weird and you're going to have to memorize. And you'll see it a ton today. Just in 4.1, we'll use it a ton. 6 to the negative 2, just to give you another practice. The negative exponent tells you to move this guy. Move him, move him, move him. So we're going to move him to the denominator. And the negative goes away when you've moved the base down to the bottom because that was his chore, that was your job, and you did it. This becomes 1 over 36. Okay, starting with number 1, this is the graphing that we're going to be doing, and you're going to see we're going to do it over and over and over and over and over. This will get to be real habit for you. The function itself is f of x is equal to 3 to the x power. This is an exponential function because the exponent is a variable. Notice that the x is the variable. So when we set up our t-table, we're going to grab the, if the exponent is an x, and it will be in all of this section, we're going to write negative 2, negative 1, 0, 1, and 2 for our inputs in this function. I've written y, Thomas has written f of x. They're the same thing. It's not a big deal. It's just an old habit I've got there. So f of x, same thing. So if we plug in a negative 2 into the x, we've got 3 to the negative 2. Just like we were taking care of up here, that negative exponent tells you to move him. So we're going to have 1 over 3 squared, which is 1/9. So when x is a negative 2, when I plug in a negative 2 there, I get 1/9 for y, for my f of x. When I plug in a negative 1, 3 to the negative 1, the negative exponent says move me, move me, move me, and that gives me 1/3. So I've got 1/3 for my second y. 3 to the 0 power, remember anybody to the 0 power is equal to a 1. And then we've got 3 to the first power, well you know that's 3. And then 3 to the second power, and you know that's 9. Don't worry too much about this, getting this right now. Get the idea here and be fine with it. Your brain will adapt. We're going to do that so many times in 4.1 Thomas's and 4.1 mine. Okay, now what we need to do is graph this function. Thomas has given you this piece that has just the first and second quadrants in it. So we're going to be based completely in the upper half of the Cartesian coordinate system on these. So with that in mind, I grab my little handy dandy graph board, and I think that I will turn it this way. Let's see what we've got. So this is the y-axis, and this is the x-axis. I've just turned it so I have more that I can deal with up here. Okay, our first point that we've got, I hope you were able to see all that. If not, I'm sorry. Our first point that we've got is -2, +1/9. So I'm going to go -2 and then go up just a teeny weeny bit, 1/9 of the way into there. So little bitty, right, almost sitting on top of the x-axis there. The next point is -1, 1/3, -1 and 1/3, a third of the way, a little bit higher. 0 says don't go sideways, 1 says go up 1. Going to go through that point on every stinking one of these graphs. That's a big deal, because whatever this number is, we're raising it to the 0 power, and we'll always get 1. If I lost you there, no problem. I'll get you on the next one. 1, 3, go out 1 and up 3. And then 2, 9, go out 2 and up 9. We're going to draw that in. This looks like it'll cross, but it's not going to. That's not the point of these exponential functions. This coming out this way is going to ride as close as it can get to the x-axis, but never quite cross it. So bring it up here, like that. And that's an exponential function. It's going to look like that. It's going to hug this x-axis. This is a horizontal asymptote. Y equals 0 is the horizontal asymptote for all of these, unless we transform them. You'll worry about that later. But 3 to the x, the ones we're going to do right now, you'll see when they're landing like this, they're going to scoot along here, getting closer and closer and closer, but never actually touching the x-axis as they go that away towards -infinity. These heading up here are going to launch forever. They're going to head, and they're heading up fast. You can see at 0, it's only a 1. At 1, it climbed up to 3 here. At 2, it was already up to 9. At 3, that's going to be 3 to the 3rd power. That's 27. I mean, that is way high up off the charts. So this is an exponential function. They will all look more or less like that. You'll see. We're going to flip it a little bit, move it a little bit, but that's the idea. It's just like a parent shape that you've got there. Okay, let's look at number 2. Number 2 is the other basic kind of shape, but you'll see it's very similar. Number 2 is f of x equals 1/2, where we start with a fraction instead of a whole number. 1/2 raised to the exponential, the variable that is an x. Set up the same x and f of x or y. And because the x is the exponent, I'm going to put my 5 numbers under the x column. We're going to later have a y up there, and we'll put them over here. But for now, for all of this section and all of 4.1, if the x is the exponent, put your little set of numbers in the x column. Okay, let's go ahead and plug these in. 1/2 raised to the -2 power. Remember, a negative exponent says move me, move me, move me. That means everybody in here needs to move. So it'll just flip the fraction. It's very much a reciprocal. So this 2 comes flying up to the top. He was in the denominator. Now he's in the numerator. And now this exponent will be a +2 because the negative, you've done that job. So 2 squared is 4. So there's our first point. Let's plug in the rest. 1/2 raised to our new point of -1. Remember, a negative exponent says move me, move me, move me. So take that denominator 2 and scoot him up to the top. And now he's raised to the first power. There's our second point. Here's the one they're all going to have in common. If we raise 1/2 to the 0 power, if we raise any number to the 0 power, we're just going to get a 1 out of that. Always. 0, 1 is going to be the pretty much kind of like the vertex point of this parent graph. It's what we're always going to be using for our known located point. Let's look at 1. 1/2 raised to the first power is just 1/2. And then 1/2 raised to the second power. 1 squared is 1, 2 squared is 4. So let's graph that. Again, Thomas has got just using the top halves there, the top half of the graph. So that's what we're going to do too. That's where it's all going to be. Let me grab my graph. I think I'll turn it again, same way. And I know this is going to get it's going to get glary for you.
Let's see if I can raise it up enough. No, it's right there in the glare, isn't it? There, let's do it like that.
Okay. First point is -2, 4. -2 says go sideways 2 and up 4. Second point, -1, 2. -1, +2. Plot 0, 1. There it is. We're always going to be going through that point. 1, 1/2, go over 1, go up 1/2. And then go out 2, up 1/4. So this is the reflection of the previous graph. The idea is, anyway, an exponential. If you've got a fraction raised to an exponential, the graph is going to look like this. It's going to come screaming down from the left-hand side, and it's going to hug the x-axis as it goes to positive infinity. So the horizontal asymptote here is still y = 0, just like the previous one. But instead of rising to the right, it rises to the left. This one will hug the x-axis as it goes out to infinity. Remember, our previous one was just the reflection across the y-axis. It'll hug as it goes out that way. So you can see on your paper the two graphs now. They're just reflections of each other. This is the 1/2 or one, well, we'll get to that in a second. This is the 1/2 one, and then the other one we looked at that does something like this, hugs the x-axis and then rises. That's the previous one, number 1. Okay, let's go to the next page. Flip over the top of page 2. And this is kind of a big deal. This is what we see in these two graphs right here. Let me scoot this down. We're good there. Okay, so when b is greater than 1, and what that means is that you've got like f of x, hang on a second, f of x equals 2 to the x power, or 3 to the x power, or 4 to the x power, or even something like 2.12 to the x power. Some whole number, something bigger than 1, raised to the x power. Then the graph is going to do this sort of thing. It's going to go through 0, 1. It's going to hug the x-axis as it goes out toward negative infinity, and it's going to rise steeply on the right-hand side. Whereas the other graph we're looking at, if it falls between 0 and 1, if the base does, like f of x equals 1/2 to the x power, 1/3 to the x power, 1/4 to the x power, that sort of thing, then it's just going to be a reflection of this across the x-axis. It's going to be climbing going that way, go through 0, 1, and hug the x-axis. So this would be, for instance, f of x equals 1/2 raised to the x power. This would be f of x equals, for instance, 2 to the x power. The steeper, the bigger this number, 3, 4, 5, 6, 7, 8, 9, the steeper this line is going to be, the steeper the climb will be. Similarly, 1/2, 1/3, 1/4, they're going to hug in here. 1/9 to the x power would look like that. It'll scream in closer, tighter. So the larger this number is, or this denominator is, as it gets as the denominator gets larger, as this base gets larger, they hug in a little tighter to the y-axis as they go up. The domain on both of these is going to be the same. The domain on any of this that's drawn, remember we're talking about what is it using up on the x-axis. It's going all the way to negative infinity, all the way to positive infinity. So the domain for all of these exponential functions is negative infinity to positive infinity. The range, doing the same kind of thing, but it's not the same negative infinity to positive infinity, but the ranges on these two will match. Notice that we're not using up any of the range, and that's why Thomas gave us these graphs without any negatives. He wanted to focus on what was going on here. So we have nothing going on in the negative range. The first time we grab this, let's look at this one. This one's going to go all the way down as close as it can get to 0, but it's never going to meet 0. Remember, it's an asymptote, and it's never going to touch 0. So we're going to start at 0, but put a parenthesis on it to indicate that we're never actually going to hit the x-axis. So it's never going to get to 0 on the range. And then how far does it go on that thermometer? It goes up to infinity. So the range on both of these, even this one, talking about what we're using up on the thermometer, it doesn't use up anything below the x-axis. If you scoot this over, it gets to 0, but not quite. So we put a parenthesis on it, and it will continue to go on up to infinity. And then the horizontal asymptote for both of them is going to be y equals 0. We're never going to touch that line. That's the horizontal asymptote. We don't have a vertical asymptote. This could slide out here, it could go up there depending on what the base number is. Ditto for this side. Okay, let us look at the next.
How are we doing here?
Nah, I'll scoot it up. Okay. Let's look at number 3. We're asked to graph each function, give you a graph there, identify the domain, range, and any asymptote. So pretty much what we just did with the previous thing. So this is f of x equals 3 to the x plus 1 minus 2. Okay, we're not going to do any numbers on this one. What we know
For this graph, scoot it over here so I can get rid of that glare for you.
What we know about this exponential, and it's an exponential function because the variable is sitting there in the exponent. That's what gives it its right to call itself an exponential, is because the variable is the exponent. This is the parent graph would be 3 to the x. So the parent graph we know is going to go through here. It's going to slide here. It's going to do 1, 3. And then 2, 9. So it's just going to go way up there and even higher than that. That's what the parent looks like. Maybe clean it up a little bit. There we go, a little bit. This belly button, this is an important point. That point is what we're going to use to do our shifting with. So let's look at what shift happens here. Same as always, this is a liar, this tells the truth. So this point, all of the points, but this is the easiest one to locate, is going to be moved. And it's going to be moved -1, -2. The opposite of that number, the same as that number. So we're going to take this place and move it to -1, -2. So we want to shift this to the left 1 and down 2, and it's going to go right there. Notice that we're not shifting it to the point -1, -2, because we're not starting at the origin. So this point, we're going to shift to the left 1 and down 2 from the belly button that sits up here. So that's a thing you got to watch out for. Although my recollection of your My Math Lab is not that big of a deal. You'll be okay with that. Crap, I used a Sharpie. Let me show you how to do this. So you just cover it with whatever you want to. Just cover it up. And then while it's still wet, wipe it off. See how well that worked? Let's try again. Oh, I see what I did. I used another Sharpie. Go, dog. Okay, this ought to work. There we go. Lovely. Okay. So you're going to go to the left 1 and down 2 from this belly button. Over 1 and down 2. There's where our new transformed exponential function will move. So we're just doing, this is going to come, this asymptote, this horizontal asymptote was 1 unit down, so will this one be. So we're going to come screaming in here, never going to touch that, and then it's just going to climb from here. So something like that. That's good enough. You're not going to have to be perfect on these. This is concept way more than detail. So we're looking for domain, range, and asymptote. Domain, still going to be -infinity to +infinity. We're using up all of the x-axis. The range, though, we move down to. We move down to from this place, but that takes us down here and down 1 more. That's where the horizontal asymptote is. So we're going to be hugging -2 along there. So the range will be -2, parenthesis, be sure it's parenthesis, because you're not ever going to hit this line. You're not ever going to get to the -2 on the range. And then we'll head up to infinity. Horizontal asymptote is always y equals. And what line are we not going to hit? We're not going to hit the y equals -2 line. So this is our horizontal asymptote right in here. So y equals -2. Okay, let's do the same kind of thing with number 4. Let's see. It's 3b, I guess. 3b looks like g of x equals -3/4 to the x power plus 4. Okay, let's start out by talking about what that graph will look like as a base parent kind of graph. 3/4 is a fraction. It's between 0 and 1. So that's going to look like the opposite of what we just looked at in 3a. It's going to come through here. It's going to hug along here. And then it's going to come up here at some height. We're not concerned about exactly what that's doing. Okay, so what's going to happen are 2 things are going to happen to this. This graph, we're going to flip. We're going to flip this along the x-axis. We're going to reflect it down here, and then we're going to move it up 4. So let's look at that a little more closely. Let's ignore the negative right now. There is nothing happening here on the x-axis, so we're not scooting it sideways. So there's no horizontal shift. We are going to raise it up 4. Because that's a shift on the y. That's the second one. First thing we need to do, though, is take care of this. We're going to flip this down. So let's do this in a couple of steps. Let's look at This was the horizontal asymptote, so it'll still be the horizontal asymptote, just it'll be reflected across, the x-axis. So flip this down. So we're going to be hugging along here. We're going to go through this point right here, which is the reflection there, and then just come screaming down here. So that is just the reflection. We're not going to shift it horizontally, and we are going to shift it up 4. So let's take that same point, this belly button, and shift it up 4. 1, 2, 3, 4. That's where we're going. So we're going to come down here. There's our horizontal asymptote right there. Sorry about that. That is not what we're going to do. So here's our belly button right here. That's this belly button moved up 4. 1, 2, 3, 4. And then we're just shifting the red one, not the black one. We're shifting the red one up. And so what we've got is we're going to rise to the right 1 unit. And there's our horizontal asymptote. And then we're bringing this red one, this arm that goes down, we're bringing it down here. So something like that. The blue is the transformed. First thing we had to do was flip it. That flips it down here, becomes the red guy, and then move it up 4. So this is the one we want. Let's see what we got about him. We've got a domain. The domain, the x-axis on the blue, the x-axis goes all the way to the right, and it'll go all the way to the left. The range, we're looking at what does it use up of the y-axis? What does it use up of the thermometer? And so what we've got happening here is this blue line will go all the way down. So this one's going to start with negative infinity. It'll go all the way down there. Where do we stop using up? Scoot this in, scoot it in, still using it, still using it. Oh, right there? Nope, a little bit higher. We actually go up to 1, 2, 3, 4. 1, 2, 3, 4. That's where we're going to stop going across the y-axis at 4. Don't include it. Don't put a bracket. We need parentheses there because this will never quite reach that point on the 4 degrees or whatever, if you want to call it like a thermometer. And then we need a horizontal asymptote. We're looking at this line that runs across. Let me grab my black one. Here we go. This line right here that we will never cross. And that is 1, 2, 3, 4. Y equals 4. It's not a coincidence that it matches the y, the height of the y. That's as far as we can go. So those match on purpose. Okay, let's look at the next problems, a couple problems. Thomas introduces you to E. That's the next thing we're looking at. E is a growth constant. It's on your calculator. Let me show you where that is on your calculator. The E key is right up here. It's in the gutter. It says e to the x power. So let's just grab E first. It's in the gutter, so hit second and then E. And you can see it says E raised to the power. So let's just raise it to the first power and hit equals. And there's E, 2.71828 It's an irrational number. It's never going to repeat. It's never going to terminate. It's a number kind of like pi to us. It stands for a value. Pi has to do with circles. E has to do with exponential growth. It has to do with growth in real life. It has to do with how many people move into a community over time. It has to do with how many people die under certain circumstances. It has to do with growth and decay, losing number of trees in a forest over time. Just all kinds of natural things that obey this rule, just like circles obey the pi rule. It's just one of our useful tools. So number 4 asks you to figure out, just play with your calculator and get E squared. So I'm going to clear that. I'm going to go after E again. Let's see. Number 4 asks you for E to the second power. So let's hit the second key and then the E key. And it says E to the, so let's put a 2 in there. You don't have to close out the parentheses if you don't want to. We get 7389005. They want it rounded to 4 decimal places. 1, 2, 3, 4. There's the 4th place. That's as far as we're going to go. This guy tells us what to do. It tells us to round this guy up. So 7.3891 is the correct rounding for that one. Let's look at number 5. 15 times e raised to the negative 3 power. You can just power through this one on your calculator. 15, and you don't even have to ask it to multiply. It knows it's going to multiply, but you got to get e in there. So second e, and it's telling you it's raised to what power. You want to put in negative 3. So use this negative, negative 3, and hit the equal sign, and you're getting 0.74680. We want to round to 4 places. There's the 4th number. 0 says, just let it go. So 0.7468 is the answer there. If you want to put this in step by step, feel free. You would do something like e to the negative 3 and get that answer. And then multiply it times 15. Times 15 equals, and you'll get the same answer. You can see that. Okay, we are going to play around a little bit with some stuff that E is used for. You can see in the next group, in the middle of the page, it says use exponential functions to compute compound interest. So, let's get rid of this for now, although it's going to be our friend in this section. Okay. We have 2 formulas we're using here. Got A equals P times 1 plus R divided by N times NT. Let's talk about what each of these things means. A is your big pot of money. That's all the money you're going to get after you leave some little pile of money in the bank for 10 years or something like that. P, that's the principal. A sometimes stands for accumulated value. It's the amount of money that your money has gained in the bank account. P is principal. It's the small amount that you put in to begin with before it gains interest. R is the rate, but it like if you're making 2.5% or 0.5%, or the Fed just went down to 0% to loan money, that kind of thing, you have to turn it into a decimal. Be sure you turn it into a decimal, and no problem, I'll show you how to do that. N is the number of times per year that this money is being compounded. Like if it says it's compounded annually, that means once per year, so we'll put a 1 there. If it says compounded semi-annually, that's every 6 months. That's twice semi-annually. We'll put a 2 right there, and actually right there too. We've got 2 places to use the N. If it says quarterly, that means 4 times a year, and we'll put 4s for those 2 N's. And then T is the number of years. The number of years that you're leaving your money there to be compounded. Okay, so the other formula that we've got here, A equals P times our little friend E raised to the R times T. PERT is a way that you can memorize it. You're not going to have to worry about memorizing it, but if you did have to. So A again is accumulated value. That's the big pot of money you get at the end of the time that your money is in the account. P is the principal. It's the amount that you put in the beginning. R is the rate, and again, it's got to be in the form of a decimal. They're going to give you like 3%. You've got to convert it to a decimal. I'll show you how to do that if you've forgotten. And then T is the amount of time, the number of years that this money is left there. Okay, these 2 formulas are used in different things. This one is used in what's called continuous compounding. Notice it does not have an N. How many times is it compounded per year? This is continuous compounding, and this is for specific amounts of compounding: annual, semi-annual, quarterly. You can even do daily. We don't mess with it in our calculations, but you could do daily compounding. So you have to know which one they're asking you for. If you're asking for continuous compounding, you use this formula. If they're asking for some length of time that it gets compounded per year, we're using this one. So let's look at what number 6 is asking us. We're investing a certain amount of money, $15,000. That would be P. That's the principal. That we're investing at 2.5% interest and under the following conditions. So we're going to invest for 7 years. You can see that in the instructions. But A says we're compounding it annually. Only once is that interest folding over. B says compounding quarterly. 4 times a year they're going to throw in the interest and start computing again. And then C is compounding continuously, which deals with the E. So let's look at the 3 choices that we have. I think I can fit them in here. We'll see. I want to be able to for you to see this. A is compounded annually. So if it's being compounded a certain number of times a year, we're using this formula. So A equals P parenthesis 1 plus rate divided by the number of times per year times NT. Let's plug in what we don't know, or what we do know. A, we don't know. Principal here is $15,000, parenthesis 1 plus. The rate you are told is 2.5%. So 2.5%, anytime you're converting from a percent to decimal, you take the decimal point and you move it 2 places to the left. So we're going to get 0.025 out of that, and that's what we're going to use, 0.025. The N is how many times this is being compounded annually, and it says annually, so that's 1 time a year. Close the parenthesis, raise it to this exponent. How many times per year? That's what N is, that's a 1, times the time. How many years? And they tell you in the instructions it's 7 years. So let's clean this up. $15,000. 0.025 over 1 is just 0.025. 1 plus 0.025 will give you 1.025. 1 times 7 is just 7. Let's put this in our calculators. So we're going to do, you can do this in one full stream. I'm kind of a fan of doing it separately, and let me show you why. Our accumulated value, the whole amount of money you're going to get, I'm going to leave this $15,000 here for right now. 1.025, put that in there, 1.025. Then we want to raise it to the 7th power. Humpy button's right here on the left-hand edge. Humpy button 7 equals. So I'm not going to write that whole number down because it even extends outside of your calculator range, but 1.188 dot, dot, dot. I'm going to close that out. Leave that in your calculator. You want it to be as close to real as possible. You don't want to round. Now what we do is take that number and multiply times 15,000. Times 15,000. So the answer, the accumulated value, you've put $15,000 in the bank, you left it for 7 years, and you're going to get 17830, and let's round to make it look like money, so 29 cents. That's how much you're going to get compounded annually. 1 time a year they roll that interest over and hand it to your account, and that's how much you're going to get. 17,000 used to be 15. 7 years later you've added almost 3,000 to it. Okay, let's look at B. Let's do the same thing with B. On B, I'll just move it over here since B is over there on your worksheet. On B, we're doing the same thing. We're compounding quarterly, so we're going to be using this formula. We know the principal, it's still $15,000. The rate is still 2.5%, so scoot it over, 0.025. N is the number of times per year it's being compounded, and that is a 4. It's 4 times quarterly, every 3 months. Raise it to the N quarterly times how many years? So let's clean this up a little bit. Leave the 15,000 there. I'm going to work on getting 0.025 divided by 4. I'm just clear the parentheses. So 0.025 divided by 4, and that gives me that number, plus 1. So, I mean, you can put it in your calculator. or you can just put a 1 in front of it. 1.00625. 4 times 7 is 28. So we're raising that number to the 28th power. It's already in your calculator, so I think I'm just going to raise it to the 28th power. Just hit the humpy button. It took my answer, 1.00625, raising it to the 28th power, and that gives me that number. 15,000 times, and again, I'm not going to write that all out. Even if I did write it, I'd be missing all the numbers that follow. I don't want to round it. You want this to be true, and every time you round, you lose value. So we've got that. Now we need to multiply it times 15,000. And there we go. That's our accumulated value if every 3 months they're going to hand us some interest into our account, make it look like money. So we get 96 out of that. $17,858.96. When we compounded annually, only once a year, we got $17,830. So woohoo, we made $28, almost $29 by getting an account that compounded quarterly. So it makes a little bit of a difference. Compounding once a year, that's where they add in your interest, versus doing it 4 times a year, cutting it down and adding it in, because this is still just the annual rate. They just break it up into 4 little groups. It's still the same rate. It's just how many times are they going to dole it out to you. It's like getting allowance or your job. If they gave you at your job all your money in January, or if they doled it out to you in even little groups every 2 weeks or every month. That's all that is. Let's look at continuous compounding, see if that's a big fat deal. Here's the formula that you'll use for continuously compounding. So A is, again, that'll be our accumulated value. The principal, still 15,000. Then we're going to take E and we're going to raise it to the rate that we're using. We've been told we're using 2.5. So 0.025 times the years, times 7 years. You can put this in your calculator in one great big gulp if you want to. I'm going to slow it down a little bit. You do what you want to do. As long as you get the right answer, it doesn't matter. So I want to raise, well, first off, I need to find out what 0.025 times 7 is. 0.025 times 7. So I'm going to raise E to the 0.175. So let me clear that. Go grab E. There's E. Raise to, that's already built into it. 0.175 and hit equals. And I'm going to multiply that times 1.19, blah, blah, blah. I'm not going to leave it out. I'm not going to take it out of my calculator because I want to turn around and multiply times 15,000. And there, continuously compounding. 68.69. That's the way, make it look like money, round it to the hundredths place. So once a year is 830, 17,830. 4 times a year gives you 70,858, about a $30 difference. And then continuously, which sounds like you should just be rolling in it, it's only $17,868. So you're only making 38 and a little bit more than the, so it's not a big deal. It doesn't make a big deal of difference. Okay, we have one more problem here to look at, I think. We got the problem on half-life. Yeah. Okay, let me get us a new piece of paper. Be thinking about things that you can tell me when we meet for class that would improve this for you. I know this is really, really rough, so I'm sure there are lots of ways I could improve it, and I would appreciate you telling me how. I like the idea that you can go at your own speed. I like the idea that you can blow this up. I like the idea that you can stop it. Fast forward through it till you get to a problem you didn't know how to do. All of that I love. Okay, so we're looking at number 7.
Use exponential functions and applications. So number 7. Let's see, let me scooch down there so you can see it. Or let's just move us down here. That's what we'll do. Where are we? Right here. Okay, good enough. Weapon-grade plutonium is composed of approximately 93% plutonium-239, Pu-239. The half-life of Pu-239, plutonium-239, is 24,000 years. That means the stuff that's working in the plutonium, the important stuff, will be half strength in 24,000 years. It breaks down to half its strength after a long, long time. So it says in a sample originally containing half a kilogram, so we've got a half a kilogram, not much. That's like not nearly the weight of a paperclip. The amount left after T years is given by that formula. So A of T, and T is going to stand for, let's see, what do we have here? T years. So how many years? In this case, we're talking about 24,000 years. So A of T equals 0.5. That's the half a kilogram that we've got of plutonium. We're looking for its half-life, and that's going to be found by taking that time and dividing it by 24,000 years. So the first one, so this 24,000 years, that's the half-life that we get for plutonium-239. Problem A asks you to evaluate the function for the given values of T and interpret the meaning in context. So we're looking for what we've got after 24,000 years. How much of this 0.5 is still strong? How much life does it have left? So 0.5 times 1/2. The time that we're talking about here is 24,000, and we're dividing it by 24,000. This is the question they've asked you. That's the question they've asked you. How much time are you looking at? This is the half-life. And I'll talk about it again when we get to B so you can see the distinction. It's a little hard to tell when they're both 24,000. So this is going to give us some information. Remember, this is the name of the equation, and this is the amount that we're going to put in if we go over there. Equals 0.5. You know that 24,000 over 24,000 gives you a 1. 1/2 to the first power is 1/2. So you end up with this half a kilogram of plutonium. Its half-life after 24,000, what will it be worth? 0.5 times 1/2. You can do this a number of ways. You can convert this to 0.5 if you would like to. You can convert this to a half. I think they want decimal. So 0.5 times 0.5 is going to give you 0.25. Think about this as if you ate half of a pizza. There's half a pizza left and you ate half of it. So you only got a quarter of a pizza. Back to this plutonium. What this says is that at 24,000 years, that half a gram that we had is now only worth a quarter of a gram. It's only got the plutonium in it of a quarter of a gram. Let's look at B. B is doing the same exact question, except we're talking about 72,000 years later. So A of 72,000, here we've got our half of a kilogram of plutonium. We're looking to talk about its half-life, and we're going to raise it to an exponent. That exponent is T over 24,000. The time we're being asked to look at is 72,000, and its half-life is 24,000. So let's keep moving on here. Here's our half of a kilogram, 1/2. 72,000 divided by 24,000, that'll give you 3. And then we're just going to grab our calculators for the rest. So we've got, I kind of prefer to show you how to back up, but you can go straight forward. You can go 0.5 times, and then this is a half also. So 0.5 raised to the third power, and you'll get 0.0625. That's the answer. But I'm kind of a fan of backing up. So I want to do half to the third power. So we know that 0.5 is the same thing as half. Raised to the third power, and I get 0.125. Then times 0.5, backing up here. We get the same answer. You do it the way that makes most sense to you. So you've got a whole lot less of your stuff left after 72,000 years, 3 times as long, because what happens is the first 24,000 it cuts in half, the next 24,000 it cuts in half again, and the next 24,000 it cuts in half again. It just keeps cutting this smaller and smaller amount in half. Okay, I think that's good for Thomas's, and I'm going to show you this twice. I'm going to show you this time, and show you this next time, because it's so important. So here's what I did. Let me get this stuff out of the way. Here's what I did. This is my worksheet. We'll look at it later. I want you to see what's behind it here. I built myself a graph. On the x-axis, I've got the days of March. On the y-axis, I've got the number of U.S. deaths due to coronavirus. They're keeping track of those. You can find them almost anywhere. Just Google it if you're interested. And what I did was I plotted on March 1st, there was 1 death. You can see that little dot there. On March 2nd, we had 6 deaths. So this scale goes from 0 by 25, so each line is about 12.5 or so. On day 3, we had 9 deaths. On day 4, we had 12 deaths. So it's almost up to the line, the first line, which is kind of 12.5. Let me show you what we've done. Today, when I'm taping this, it's the 23rd of March. And look at what this has done. Look at this curve. You recognize that? That's an exponential curve. That is what we're talking about here. That is the curve that we're dealing with in 4.1, exponential functions. That means what I've looked at here is that we're doubling in deaths every 3 days, just approximately. Sometimes it's a little faster, sometimes it's a little bit slower. But we're pretty consistent right in here. We're doubling every 3 days. So we can expect that to continue. Certainly deaths in this country don't seem to be currently the biggest problem. It's hospitals here on the 23rd. You'll be looking at this probably a week from now. I wonder what our biggest problem will be then. We're worried now about, enough PPE, enough personal protective equipment. We're worried about having too many people in the hospitals needing care and not enough beds, not enough nurses, not enough doctors, not enough ventilators, not enough respirators. This is bad enough, but more of those people, more than this, will die if we can't get them in the hospitals. So next time you say, what do we use this crap for? Right here. So you can be a smart person. You can be well aware of what's going on in this country right now and what's going on in this world right now. And that's about it. Bye.